Welcome back, ChemStars. Now we're on Level 1 Homework, page 9. So the first problem, it says, the reaction between potassium chlorate and red phosphorus takes place when you strike a match on a matchbox. If you were to react 52.9 grams of potassium chlorate with red phosphorus, what mass of tetraphosphorus decoxide, now there's a typo there, you know it's not decoxide, right? It should just be decoxide, would be produced. Okay. So let's go through, look at our Bca table. Now this one isn't balanced, so we got to make sure we balance it. So when you're looking at it, the one thing you can see is that we've got an O3 and an O10. What's the least common multiple between 3 and 10? The smallest number they both go into. Well, 10, 20, 30. We've got to get 30 oxygen on each side. When I do that, that means I got to get 10 potassium, 10 chlorine, and that gave me 12 phosphorus. I got to get 12 phosphorus. So there's your balancing. Now let's set up a Bca table here. We know that before the reaction starts, we have some number of potassium chlorate moles. They gave us grams in the problem. We're going to have to do a little calculation here. So KClO3, go to your periodic table, and KClO3, we've got potassium, 39.01, chlorine's 35.45, and then 3 oxygen. That gives us a molar mass for potassium chlorate of 122.55. So 122.55 grams make up a mole. We're going to just do our math right here. 52.9 divided by 122.55, and we're going to get 0.431. And that's how many moles of the potassium chlorate we have. So 0.431. Before the reaction starts, we're assuming we have enough, or we'll just say we have excess red phosphorus. And before the reaction starts, there are no products. Remember that we're going to be pulling all of our mole ratios from this balanced chemical equation right here. This is my recipe, but down here, the Bca table, those are my ingredients, what I actually have. So during the change, what's going to run out first? This one right here, the potassium chlorate. I'm going to use up all 0.431 moles, and there'll be none left over. I'm calling that my limiting reactant. And then, they didn't ask me anything about this. I'm just going to skip it. What they wanted to know about was the one product, the tetraphosphorus decoxide. How much of that will I be creating? I'll be creating exactly that coefficient number over here, the 0.431, times the ratio of the unknown to the known. And I'm pulling that mole ratio out of the balanced chemical equation right here. So we're going to take our number times 3 over 10. So take your calculator times 3, divide by 10. We're going to end up with 0.129 moles. So 0.129. That's how many moles we created, but they don't want moles, they want grams. So we got to find the molar mass of that and multiply through. Okay, so P4O10. Let's take a look at our periodic table. Look, here's P4. Phosphorus is 30.97. O10, 283.88. So times 283.88 grams per mole. That's supposed to be an 8, sorry. So times 283.88. And that's going to give us 36.76. 36.76. Now we want to look for sig figs. In the original problem, the uncertainty comes from this measurement, and there are 3 sig figs. Let's do 1, 2, 3. Look to the right. The 6 will round that 7 up, and we get 36.8 grams. There's your final answer. Okay, so why are we going through all this trying to figure out grams to grams? Well, this is what you'd really be doing in a chem lab. You wouldn't know moles. You could be measuring grams using a scale. You'd be doing the reaction and then measuring the grams back afterwards. Let's try number 6. Okay. So consider the following unbalanced chemical reaction. So we know that we need to balance this. I did that for us. Saw a lot of 2s and 3s. That usually implies you go into 6. So we have 2 europium solid atoms plus 6 hydrofluoric acid gas yields 2 europium fluorides plus 3 H2 gas. And europium is one of those kind of weird ones on the periodic table, one of those lanthanides in the F block. Definitely something you wouldn't usually encounter. Okay, so we balanced it. Now we need to determine the volume of gas required to make this many liters of helium, or hydrogen, sorry. That means we have to kind of work backwards. So stick with me for a moment here. I'm going to walk you through this. We know that before the reaction starts, let's just focus on this side right here. Before the reaction starts, we don't have any products. They told us that we're making 6.93 liters. That means we have the ability to figure out this final number of moles. So we're going to take our 6.93 liters of H2. We're going to cancel liters and go to moles, and you end up with 0.309 moles. So we know that the final product here, we're kind of going to work backwards, is equal to this. We know I started with none, and I have this much when I'm done. Let's look to the mole ratio then, unknown to known. Well, I know that it's backwards, but you see how the colors are going to cancel each other out. So some number times 3/6 will equal 0.309. So how do we solve for that question mark? Just do a little quick simple algebra. So question mark times 3/6 equals 0.309. So with your calculator, so 0.309, we're going to multiply by 6, divide by 3, and you get 0.618. So that question mark is 0.618. So that's my coefficient. I must have used up exactly that amount of hydrogen fluoride. Okay, but do they want to know the moles of HF? No, they want to know the volume. So we're not done yet. Now, did I do that part ahead of time? No, I didn't. So let's just kind of come over here to some of the scratch work. Okay, so we know it's 0.618 moles. I'm just going to write it right here. I know it's not on the right spot. Just go with it for me here. So 0.618, oops, 0.618, that's moles over 1. We want to get rid of moles and go to liters. So 1 mole, they wanted volume, so that's going to be times 22.4. So we have 0.618 times 22.4. We're at 13.84, and we need 3 sig figs, so 1, 2, 3. This is going to be 13.8, so 13.8 liters. That's how much of the HF gas we would have needed to react. Okay, now let's look at our last problem here. Oops, let's see. Our last problem. It says aspirin, C9H8O4, is synthesized by reacting salicylic acid, C7H6O3, with acetic anhydride, C4H6O3. These are a bunch of organic compounds. If you want to become a pharmacist or a doctor, this would be a good elective to take next year, organic chemistry. The balance equation is this. Whew, thank goodness they balanced it for us, and all those coefficients are 1, so that's nice. They're asking us, though, what mass of acetic anhydride is needed to completely react 1 times 10 to the second grams of salicylic. Now we're doing a little scientific notation test here, Anya. So 1 times 10 to the second, well, move decimal twice, 1 times 10 to the second is actually 100 grams, 100 point, if you want to get sig fig technical here. Okay, so let's kind of look at the scratch work before we get too far into this. Before the reaction starts, we don't know much. We know there's no products, and we know we must have some moles of the acetic anhydride and some moles of the salicylic acid. Well, they told me grams. I have to do a little bit of work here to figure out this number, but I do know I'll use up all of that. That's going to be my limiting reactant for this part of the problem, and there'll be none left over. And then they're asking me to solve for how much I must need of the other compound. Well, we can see their mole ratio will be 1 to 1. It'll be the same number of moles once I get there, but moles isn't that useful in a chem lab. They want to know how many grams, so we have to just do some molar mass work here. So let's figure out first how many moles of the salicylic acid we have. That's the C7H6O3. So C7H6O3. Now where did I write that one down? Here it is, C7H6O3. So here's my work. Hopefully I did all those numbers right. 138.13. So we've got 138.13 grams make up a mole. So if there's 100 grams, I've got less than a mole. So 100 divided by 138.13, and that's going to give me 0.7239. We'll keep that number in our calculator. So I'm starting with 0.7239. I know that I'm going to use up exactly all of that 0.7239, and there'll be none of it left over. So how much of the acetic anhydride do I need? Well, I can say that I'm going to be using up that 0.7239 times the ratio of them, which is 1 to 1. So if I started with a number and I used up that number times 1 and there's none left over, what must that initial number be? Exactly. It must be the 0.7239. So if I have 0.7239 moles of acetic anhydride and I want to figure out how many grams it takes, I need to multiply by the molar mass. An acetic anhydride is C4H6O3, so get out your periodic table. We need to find C4H6O3, which I did right over here. And that molar mass is going to be 102. Oh, is that a 9 or a 1? Oh, let's check our math here. Okay, so 4 times 12.01, 48.4, plus 6.06, plus 48, 102.46. Hold on. I need to double check my math here. And we're back. It's 102.10. I don't know what I did before. This right here, though, is a 1. So it's 102.10. So 102.10 grams. So we need to take our 0.7239. Now, to make it better without any uncertainty, let's just get that number back. So 100 divided by 138.13. That's that 0.7239 number, times the molar mass, 102.1. That's going to give us 73.915. 73.915 grams per mole. And if you look at the original problem, there's 1, 2, 3 sig figs. So 1, 2, 3. Oh, this should actually, you know what I'm trying to say with sig figs. There should be 3 sig figs in the final problem. 1, 2, 3. Look to the right. So my final answer is 73.9 grams of my acetic anhydride. Okay, that's the end of page 9. If you've got any questions, reach out to your teacher, send me an email. Maybe we'll try and open up a discussion board post on Google Classroom and try for a Google Hangouts. Bye guys, have a great day.